All right, today we're going to be doing a lecture on differential equations. So to start off, so differential equations are essentially this an equation that has one or more known functions of x, and then and an unknown, like one or more unknown functions of x and its derivatives. So a differential equation could look something like this. It could look like a y plus a known function of x. I'm going to call this p of x, or y prime, sorry. A known function of x is p of x times y. And this is equal to a known function of x cubed x. So this is just an example of the differential equation. I could have maybe, I could take it a step further. I could say like y triple prime plus y to the power of y prime equal like q of x. This is another example of a differential equation. These are all examples. And essentially what it is it's just, it contains y, which is our unknown function of x. And we compare it to its derivatives and known functions of x, and we can actually solve for y in a lot of cases. So I'm going to go over basic classification of differential equations and like how we can see what kind of differential equations they are, and how to solve a specific type today. So there are two types of differential equations. There are ordinary differential equations and partial differential equations. So ordinary differential equations simply deal with ordinary derivatives in 2 dimensions, whereas partial differential equations deal with functions with several inputs and can have partial derivatives in multiple directions. So today I'm just going to be focusing on ordinary differential equations because they're a lot simpler. So there are types of ordinary differential equations, and we actually classify them by what's the order of the equation. Just like we classify a polynomial by its highest order, like when I say x squared plus x plus 3, that's a second order polynomial. Well, in the same, using the same logic, a y double prime plus y prime plus 3 equals y. That's a second order differential equation because the highest derivative is the second derivative. So today I'm going to be just focusing on first order differential equations. I'm going to go over just a couple of types. So one of the most simple types of first order differential equations is simply an equation that says y prime equal my function of x. And my function of x is going to be given. So an example could be like dy dx is like ln x, and I just have to integrate ln x to find what y is, right? That's one example of a simple differential equation. But we can take it a step further and we can say, okay, well here's the type of linear differential equation. So the linear differential equation is one that says it takes place in the form y prime plus some function times y equal another function. So this is a linear differential equation. I'll write that here. Okay. Then we have also separable equations. These are actually pretty easy to solve. So separable equation basically says that y prime equal a function of x times a function of y. And we've actually done this in calculus already, in calculus A, B, and BC, where if we have like dy dx equal e to the x times e to the y, we can separate our variables and integrate with respect to y and x, as long as we keep the y's on one side and the x's on one side. But so this is another kind of equation. Okay, so a third kind of first order ordinary differential equation is an exact equation. So an exact equation is actually, it has partial derivatives in it, but it's actually classified as an ordinary differential equation, and I'll show you why. So an exact equation basically says that we have a function, and we'll call this like m, and it has two inputs, x and y, times dx, plus another function, let's call it n, that has two inputs, x and y, times dy, this is 0. And so this is actually, this uses the property in multivariable calculus of the total derivative. That says the total derivative in multivariable calculus, okay, is basically this. It's basically that if I take the partial derivative of my function with respect to x times dx plus the partial derivative with respect to y times dy, is this basically the equivalent of differentiating my entire function completely. And so you see how this is kind of similar, right? Maybe I could call m of x, y my partial derivative of f with respect to x, and this is partial derivative of f with respect to y. But this is actually classified as an ordinary differential equation because ordinary differential equations, this has just an ordinary dy, ordinary dx, and a lot of the times they have both y's and x's in the equations. So I'll write that here. This is an exact equation. We have two more types of equations. There's actually a lot more than just two more, but these are kind of the five main that we encounter in first order differential equations. There's also homogeneous equations. And a homogeneous equation is essentially one that is, homogeneous equations and exact equations are actually really, really similar, except an exact equation is just a specific type of homogeneous equation. So this is actually a homogeneous equation, but an exact equation is a specific part of that where we essentially have the partial derivative of x times dx plus partial derivative with respect to y times dy is 0. So these are very, very like similar types of functions or equations, but they just differ in the sense that sometimes m might be a partial derivative and sometimes not. Okay, and the last one is one that I'm not even going to get into, but it's just a Bernoulli equation. So it's basically essentially very similar to a linear equation at first, but here we have a complicated factors because now we have like y to the n essentially, and so that complicates things a lot. Okay, so those are all the types of first order differential equations, but I'm actually going to go into how to solve one of them in particular, and that one is the linear differential equation, because the linear differential equation is actually the easiest to solve, apart from, of course, the separable equations. So the linear differential equation, as you can tell, you can't just integrate immediately, right? You have a dy, dx, and a y, and so you can't really solve that right off the bat, right? So I'm going to rewrite this. So dy dx plus p of x times y equal q of x. Okay, so we actually have to use a couple of properties and a couple of rules that we have in ordinary calculus, such that if we use let's just like look at some of the rules we have, right? Some of the rules that we have for differentiating things, like if I have u times v, that's just going to be u prime v plus v prime u, right? Okay, so do you notice how that kind of looks something like this? If I change, let's just say I change my u's to y's, right? I have y prime times v plus v prime times y. Notice how that kind of looks similar to this, right? I have y prime times, maybe let's just call this could be another function too, right? We could divide by q of x, and it looks like another function. And so now this actually is essentially the same thing, except basically v here is just another function of x. We don't know what it is, right? It's an unknown function of x. And so the goal to solve an equation like this is to essentially try to convert it into this form right here. We want to get from here to here, right? Because we have a y prime and a y multiplied by functions, just like we have a y prime and a y multiplied by functions. So our goal is to get to there. So how are we going to do that? Well, let's basically define an arbitrary function, and we'll say that, let's call this arbitrary function mu, right? Mu of x. And we want this function mu of x to have the property such that we want it to have, if we mu of x times y, the derivative of mu of x times y is mu prime x, right, times y plus y prime times mu of x. That's just the definition. But we want the property that we want it to have is if we multiply the entire equation essentially by mu of x, right, we get mu of x times y prime plus mu of x times p of x times y equal mu of x times q of x. Okay, we essentially, do you see how this is kind of similar to this, right? This is really, really close. These two are extremely close, except for one thing, right? Except for, instead of just y times mu prime of x, we have y times mu of x times p of x, right? It's essentially the same thing what we've written on the top and the bottom. But the one thing we want to do, and we can actually do this, is we can say, I want mu of x to have the property such that mu prime of x is equal to mu of x times p of x. We can actually do that, right? We can actually define, hey, this is what mu of x is, essentially. So we can say that mu of x, essentially, we basically define the properties. Okay, so now that we've gotten there, now what we want to do is essentially we want to multiply. We have already multiplied our entire function by mu, right? So we can do a little bit of algebraic manipulation, so I'm going to rewrite this here. I can say I want to add u prime of x, y, and subtract mu prime of x, y. And I want to add again u prime of x, p of x, y equals, and then my other side. I just added, I added and subtracted the same thing, so I'm just doing that. Okay, so now that we've taken a look at this right here, do you guys see that this here is mu of x times y prime plus mu prime of x times y, which is just d dx of mu of x y, right? That's essentially what this is right here. So great, we've actually isolated a part where we can define it as what we wanted to before. So this right here is d dx mu of x times y. And now here we have a common factor, right? We have y, and we can factor out, what is that? Mu prime of x, mu of x, p of x, minus mu prime of x. Okay, so now, we have this and we have this, right? Now, well, what do we do from here? Well, do you guys notice how when we define what the relationship between mu and p, right? Do you guys see how if mu prime of x is equal to mu of x, p of x, then mu prime of x, p of x minus mu prime of x is just 0, right? That entire thing just goes to 0. So that actually helps us. And so now we can actually just write the entire equation like this. Okay, so there's our simplified equation essentially, right? That's great. Now we can essentially just integrate both sides and divide by mu, and so now we have solved for y essentially, right? We have mu of x, q of x over mu of x. Okay, that's awesome. We just solved for y in our equation, but we only have one problem, is we have no idea what mu of x is. I just came up with some random function, and I still don't know what mu of x is, right? I made a definition for it, but I've never actually defined what it is, so I cannot actually solve my equation just yet. I have to go one step further. So I've actually isolated y in this case. I've isolated y to be a function of x, and it's this crazy, integral of with divided functions. So now what I want to do is, how am I going to define mu of x? Well, the way I define mu of x is I go right back to my property, right? I go back to my property that mu prime of x is equal to mu of x, p of x, right? Okay, and so I want to solve for mu of x. I want to find what it is, so I can divide by mu of x, right? And so I get mu prime of x over mu of x is this. And in order to solve for mu of x in a case like this, I actually have to use, I'm just going to integrate both sides, because I can use a u substitution such that u is mu of x and u du is mu prime of x dx, right? And that's got great. We have mu prime of x dx right here, so we just say integral 1 over u is equal to integral p of x. Okay, so now essentially I've simplified this to just ln mu of x is the integral of p of x. So we know that mu of x is e to the integral of p of x. Okay, so now we've actually defined what mu is based on p, which is in our original function. So now we can actually fully solve for y in this case, and so now y here is just the integral of e to the integral p of x times q of x over e to the integral p of x. And there is our full solution for y in that specific ordinary equation. And so this is actually the simplest possible. This is like the simplest equation basically that you can solve. They get a lot more complicated as you go into the higher orders, or as you maybe just encounter obscure equations. But this is just one example of how you would encounter a problem like this in a differential equation. Okay.